Welcome to the presentation of why SolidWorks is the ideal choice of machine builders. To demonstrate this, I will take the example of a cane crusher and walk you through the design process. Shredded cane is fed into these huge crushing mills to obtain juice, which is further processed to form sugar crystals. In our presentation, we'll see how SolidWorks will help us in designing these mills with the help of blocks, 2D layouts. Automate your design changes with the help of top-down design approach, design library, as well as validate your designs with SolidWorks simulation and ease of creating production drawings. Most of the time, a machine design process starts with a layout. We too are starting with a concept. 2D blocks in SolidWorks can be added to our design library. Just by dragging and dropping them from the library, a quick layout can be formed. It also helps us to simulate motion between relative components. We have just pulled in a side cap, and defining relations are pretty simple and easy. Just by selecting two 2D entities, SolidWorks will automatically pop up all the possible relations between the two geometries just beside the mouse pointer. This saves a lot of our time as well as it increases our productivity. We have already called in the pillar and the side caps. Next, we would need to have a top cap and few other rollers. 3 key rollers will be in triangular formation to crush the cane, which are driven by gears on their shaft. Fourth one would be a feed roller driven by motion of others. Layout blocks can be colored for better identification. Motion of the 2D rollers is defined by the traction relation between the blocks. You will also be able to define other relations like cam, follower, and belt chain relations too between blocks. Blocks thus used in the layout can be easily converted to SolidWorks parts, either on the plane they exist or on a projected plane. Let's go ahead and build side cap part with the help of SolidWorks close counter selection tools. We will add different thickness to different counters. Now this counter would have a thickness of 380 mm along the mid plane, and the next counter will have a thickness of 420 mm along the mid plane. Standard and regularly used features can be added to our design library so that they can be simply dragged and dropped with necessary inputs. Let's now form the side cap arm and the guides where bottom bearing slides. We have just formed the side arm. We'll just go ahead and drag in the guide feature from the design library. The necessary inputs in this case would be a sketch point, preferably origin, and couple of edges that would help us in locating the face of the pad onto the bottom as well as the guide edges. To round the sharp edges, we'll take help of SolidWorks Fillet Expert, which would help us in selecting large number of edges in one go. Now in this case, we have picked more than 140 edges and we'll get filleting done in all those edges with a single mouse button click. Pillar assembly is already built and ready to be placed onto the main assembly. We'll just go ahead and align the pillar assembly with respect to different planes. Since we have built the side cap as a projected part, we can easily drag the side cap from its existing location and mate it with the assembly using few advanced mate options. Using the layout reference, we'll locate the bottom bearing. Layout sketch can be switched off or on easily. Standard components from the design library can be dragged and dropped, and they take automatic mates with the place you want them to get related to. I would like to drag your attention on the bottom bearing back face. There is no guide as in side cap. We can easily indent the existing guide onto the bearing back face to speed up the design process. Indent is a real powerful feature that would help us to form the existing guides from the side cap onto the back face of the bearing bottom. We need to fasten the side cap onto the pillar. Let us use Hole Wizard to drill the holes first. SolidWorks toolbox is highly customizable as per the machine builder's requirement. As I have built my own standard for this presentation, customizing the hole sizes, fasteners and gears. To drill a hole at the center, you just need to go closer to the curve or the circular edge. It automatically gives you the center point snap. You want to drill the hole at the center, just pick the center. Mouse gesture gives access to 8 of the most commonly used commands and is an example of SolidWorks' intuitive and innovative user interface. Smart fasteners automatically populate the exact required fasteners in terms of size and numbers. Also helps us to add the necessary accessories later. Same pillar assembly is going to support the other end of the rollers. We will mirror the assembly. Within the same mirror wizard, we will be able to create new LH or RH versions of the component if required. After mirroring the pillar assembly, we need to assemble the rollers. Instead, I will create a new roller within the assembly using top-down design approach. I will create a new part within the assembly and name it as roller. A roller is of standard cross section, hence I have a block already added to my library. I will import the block onto one of the relevant sketch planes and constrain it with respect to assembly. I will open newly created roller to add its crushing threads, which is again as simple as drag and drop from the library. To do cost and weight analysis, one can apply material to SolidWorks parts and verify its weight and CG. Let's go back to the assembly. The assembly has been updated. Increasing the spacing between the two pillar assemblies will automatically resize the rollers. SolidWorks' strong top-down design will help machine builders in achieving necessary design automation. Finally, assembly is completed with all the 4 rollers. You can see SolidWorks standard toolbox containing the key bought out items like bearings, bolts, screws, gears and others. I'm accessing my customized library to show how easy one can get the necessary gears with design inputs like module, number of teeth, gear width, etc. I have already assembled my customized gears and you can see how they drive the roller motion. SolidWorks supports configurations in parts and assemblies, enabling us to save the product variations within the same file. I have got two configurations, one with and other without mannequin, just to show how mammoth the machine is. It is very easy to create drawings in SolidWorks. On picking a template with predefined views, SolidWorks will automatically get all necessary drawing views. Dimensions used to build the part can be easily called in. It gets imported in well-arranged format. Even if dimensions are not arranged, auto-arranged dimensions will come handy in arranging dimensions. Section views can be created within no time, and rapid dimensioning will help us in placing new dimensions on the drawing sheet. Detail views will help us in highlighting on particular region. Detail views would dynamically update with the region as well as the location. It is time to validate design of the pillar subassembly which bears the entire load of the rollers. 4 rollers are heavy and directly transfer all their loads to the pillar. Pillar gets grouted onto the ground. Rollers' individual weights are considered to be acting on the respective interacting faces. Remote loads are considered for bottom rollers. Pillar and rollers are of cast alloy steel. Material applied in SolidWorks are automatically transferred to SolidWorks simulation. Contacts between parts in pillar subassembly are treated as bonded. To solve the problem, right-click on the study to run the analysis. SolidWorks will automatically mesh the model with default plots like stress and displacement will be generated. Let's have a look at the factor of safety plot. Minimum factor of safety is 15, hence design is safe. Further, one can use optimization study in SolidWorks simulation to reduce weight and cut down on material cost. As in case of parts, to generate an assembly drawing, we pick the template. View palette will help us to drag and drop standard views. Views can be later scaled to our requirement. It is easy to insert a bill of material. The bill of material template can be customized to call material, cost, weight, and other properties. It's also very easy to balloon the drawing views. Assembly BOM is completely associative with the drawing view. Any part picked from the BOM will get highlighted graphically, and corresponding row will get highlighted if we pick any part graphically. These are few of many other functionalities that would help machine builders. Assembly visualization tool that would act exactly as an interactive bill of material also helps us with design change analysis, cost approximations, and much more. SolidWorks sustainability will help us to design eco-friendly products. Feature works to recognize features in imported dump solids. Design checker to check and auto-rectify production drawings as per the company standards. T-feature helps us to communicate and share designs by hiding critical and not necessary design intents. Express tools like DriveWorks Express and DFM Express for design automation and manufacturability check. Tool Analyst will assist us with tolerance stack-up analysis. PhotoView 360 will generate high-quality rendered virtual realistic images. SolidWorks Motion to do kinematic analysis. This is the final design. After validating design using SolidWorks simulation and SolidWorks sustainability. This image is rendered using PhotoView 360. Many thanks for watching this presentation. For more information, log on to solidworks.com.